Segment 25, Graphical Display of Spectra and Spectral Types. We already discussed the issue of how difficult it is to follow spectra that are displayed in the form of color bars, and this illustration of the spectrum of an M star makes that very clear. The top bar shows the spectrum, the colors of the rainbow type spectrum with black lines in it. This is very hard to interpret. If you plot instead intensity along the y-axis while going in wavelength along the x-axis by measuring the actual brightness at each point along this color bar type spectrum, you get a graph like the one at the bottom. And this does a much better job of informing you what's going on. It shows you the depths of the different absorption lines and the variation of the broader features much more clearly. On a particular individual line, you can see how this is done. The photograph at the top shows you the density of the spectrum on the photographic plate, as this was originally taken like a CCD would be today, and in a grayscale form, and it's plotted along the bottom how that intensity varies along that spectrum, so as a function of wavelength. And you see that on the left it's white, and that's almost 100% of the light, and then in the middle it's black, it's almost 0%, and then as you go over to the right you see it getting back to white again, and you see that this grayscale at the top turns into this gentle curve at the bottom. And that's the way we'd like to display them to get some understanding of what's going on with the lines. So let's talk about what we know about how to use spectra to get information. We started this process when we understood about atomic transitions and about absorption of photons or collisions exciting atoms to higher lying states, and then when after some period of time the electrons would jump down to a lower bound state and a photon of a particular wavelength would be emitted, and this allowed us to tell one atom from another. It also gives us information about the temperature of the gas that's involved because of the amount of energy that's required to get to a different state. So this plot is showing us the energy levels of the neutral hydrogen atom. The lines we see at the visible part of the spectrum start from level 2 and are absorbed up to states higher than that. And if you have a very, very cold gas, all of the electrons will be in the ground state in level 1, and the lines from level 2 will be very, very weak. As you heat the gas up and the collisions in the gas become more forceful, the physical collisions can excite the electrons in the atoms up to the level 2, and from level 2 they can absorb photons then that produce these spectral absorption lines that we see in a stellar atmosphere of a warm star. So as the temperature gets warmer and warmer, more and more of the atoms have electrons in level 2, and that absorption can get deeper and deeper from a given gas. If you go too far, however, and the collisions are too powerful, it starts to ionize the gas. It starts to actually separate the electrons from the protons, and then there are very, very few neutral hydrogen atoms around. So instead of seeing strong absorption from level 2, you see no absorption at all. If you try to make a plot of line strength versus the temperature of the gas in the stellar atmosphere that you're looking at, it would wind up looking like something like this. At very low temperatures, where all of the hydrogen is in the ground state, the lines would be very weak. Then when you got to higher temperatures, the lines would get stronger and stronger until finally you started ionizing the gas at temperatures above about 10,000 degrees, and then the lines would get successively weaker as the temperature got higher and higher. One of the consequences of this is that, apart from at the peak of the line strength curve, for every given line strength there are actually two possible temperatures that the gas could have. So how do we tell the difference between a star with moderately strong hydrogen lines that's cool and a star with moderately strong hydrogen lines that's hot? So in this case, between a star that's at almost 8,000 degrees and one that's at almost 12,000 degrees. The answer is we have to look at something else. So if we make a similar plot for ionized calcium, we see that for very cool stars, the ionized calcium lines are very weak because most of the calcium is neutral. And for very hot stars, the ionized calcium lines are weak because the calcium has had 2 electrons removed from it, so singly ionized calcium is not very abundant. Then, if you look at a hydrogen line of intermediate strength and you see that there's no calcium lines at all, you know that it's a 12,000 degree star. Whereas if you look at a hydrogen line of intermediate strength and you see calcium absorption, then you know in fact that it's more likely to be an 8,000 degree star. And that's how you tell the difference. As you look at absorption lines from a series of different atoms, you build up an overall picture that allows you to estimate far more precisely the temperature of the atmosphere of the star and over the whole range of possible stellar temperatures. So here you see some of the different indicators and how their line strengths vary with temperature, looking at neutral helium and ionized iron and even a molecule, titanium oxide, allows you, by looking at several different species, to fairly precisely determine the temperature of the gas in the atmosphere of the star, what we know as the spectral type. Now, originally this was done empirically, that is, before the whole atomic physics was understood, people just sorted the spectra by how strong the lines were. And so what you see here is a set of spectra going from O stars, which are the hottest, up at the top, down to M stars at the bottom, which are among the coolest stars. And you'll notice that the letters are shuffled, and that's because the A stars have these very prominent hydrogen lines, B stars have somewhat less prominent hydrogen lines, and that's how they were ordered originally. But once we understood the physics, we could order them by temperature, and that's the order we have now. O, B, A, F, G, K is the order in decreasing temperature. If we plot these spectra the way we'd like to in more quantitative terms, you can see very strongly how this variation in the hydrogen lines go, with having weak hydrogen lines at O, very strong at A, and then getting weaker as you go to cooler temperatures. And when you get to the M stars, you have this very different looking spectrum with all of this up and down that's caused by molecular lines, which is very different. You'll see in the K and G stars, you'll see some singly ionized and neutral atomic lines as well coming into the mix. So here's just an illustration now of the very late M stars. These are some of the stars that are brown dwarfs that we talked about recently, and these have even more exotic molecules in them in some cases. The work in this area of spectral classification started with an astronomer named Annie Jump Cannon, and she made a survey of stars all over the sky using a special device called an objective prism, where a prism was stuck in front of the photographic plate, and it, instead of taking images of the stars, took spectra all along. These spectra are very small and fairly low resolution, but they're actually enough to be able to classify the stars fairly accurately. I've looked at the original Annie Jump Cannon plate material, and as a class exercise when I was in graduate school, had to classify some of these stars. And it's amazing how well you can do with this kind of material. So she set up the original classification system, which then got elaborated once the atomic physics was understood more thoroughly. So now we have two ways to determine the temperature of a star. We can do it from the peak of the blackbody curve using Wien's law, which we talked about before, and this works very well as long as the star is not obscured by dust that might change its color. And so for kind of broad brush measurements of stellar temperature, we often use precise measurements of the color to tell the temperature. It's very hard to find the peak of the curve, but you can calibrate the relative flux in the red and the blue as a function of temperature pretty well, and that can be done then with precise measurements with modern CCDs to get stellar temperatures. But a more robust way to do it, even in the presence of dust that might change the color of the star and make it look redder, is to use the spectral lines, and that's kind of the gold standard for measuring spectral type or temperature of the stars.